So let's get started. So formal lecture included today, I guess. So the correction from last time. So the different tension dP is related to different charge up to the string coupling constant. So this is a relation I missed last time when I talked about the zero quantization condition. Unfortunately, I didn't print out the latest lecture note. So I made a huge revision in the lecture note. You should take a look at the, I think I put the latest one in the Dropbox. Not Dropbox, sorry, e-learning. So that you can take a look at the latest version of a note. Yeah, I think I hope it's okay. And then, so where were we? So yeah, yes, 13.3. Hopefully you can take a look at the 13.3 on the lecture note. This is the correction, and also for the different tension is indeed so tension dP brane is the mass divided by the p dimensional volume. So therefore, this is proportional to this is I mean, so okay, so therefore the volume, so therefore it should be proportional to 1/2 pi string length to the p plus 1. So this is the what you expect from dimensional analysis. And indeed, what we have done is indeed from the classical line reduction for M3 to B to A. So M2 divided on S1, you get that F1, and the M2 is reduced to D2. M5 on S1 will become D4. M5 becomes an S5 brane, and then of course classical line monopole, and then KK momentum. And if you assume this is the 2 pi Planck length to the cube, and then so we use the relation between Planck length and also the string coupling constant. Then what you have is this is 2 pi GS squared 2 pi string, and then here you have 2 pi GS 2 pi LS 5. Oh, sorry. No, what I'm writing. Sorry. The cube. And in the middle, you have, sorry, I don't have so much space to write down the same to the 5. Okay. Same to the 5. For volumetric, G is not involved, so you have 2 pi LS squared, and you just multiply the length of the M0 circle. And then 2 pi divided by 2 pi LP cube. You have the same thing, but instead of here, you have M5 brane tension. So this is all tension, different tension of extended object. So that I didn't explain that I missed this point. So this is different charges. And this is tension. And of course, R is equal to GS LS. That's what we have learned last time. And also, the so LP, and there's a relation between LP and LS. LP cube is equal to R times LS squared. And if you use this relation, you can obtain this kind of a relation. Yes.
You put the natural laws of differential geometry in your
Oh, sorry. Then let me put it in now. In that case, I mean, this is the cost of the teaching 2 courses. Okay, then let me put it now. Sorry. Yeah. I need to log in first. Oh, okay. So I just mix up everything. Sorry. Yeah, now I put the latest lecture note. Let's get rid of delete. And also, then differential geometry course, I didn't put the latest lecture note in that case. Sorry. Then, okay. Sorry. Then I think I mix up to think, okay. Let me do it now, I guess. So now I think you have the latest lecture note, I guess. So that the GS LS. So we use this relation to obtain this kind of relation. So okay, yeah. So that the you have correct dimensional formula. Yeah. So correct dimensional formula, and then you can check. So as I mentioned, dp. Sorry, mu p times mu 6 minus p. So the brain charges is equal to 2 pi z up to, I say, 2 pi kappa 10 squared. Where kappa 10 is I already forgot. It's the, what was that? Kappa 10 is, oh yeah, kappa 10 squared is equal to 2 pi plus to the 8 divided by 2 pi. And that's what we have, what we're supposed to have. Yeah. Okay, sorry, and then you can check this Dirac quantization condition by using this table, and you just appropriately normalize as by GS, and then you get the correct Dirac quantization condition type 2A. Yeah. Okay, so that's the what I missed last time. Yep. So now, we just introduce. So when you take, as I mentioned last time, so when you take GS is strong, so string coupling constant limit, so somehow magical phenomena in string theory occurs. So type 2A if you take the, so which is on dimensional dimension, if you go to the, if you go to M theory, you have an 11 dimensional, and the radius is proportional to GS coupling constant. Some magical property will show up, and then so it's low. So the low energy effective action of this one, low energy effective action theory is 11D supergravity. So that's a recap of last time, and then so this has the 3 form, which electric the M2 brane and M5 brane. Electric object, it is a magnetic object that couple to this 3 form. So that's the upshot of last time. Yeah, so, and then this M theory is very mysterious theory, but if you assume the existence of M theory, one can explain lots of things. And then you can see lots of new phenomena. So that's the recap of last time. Okay, so now we will see lots of, and then so 2A, 2B, type 1, and then what we are doing is the heterotic O, heterotic E, M theory, 11D supergravity, and we know this one is TDO, and this enjoy STL. So last time we talked about STRT. Did we? We did, right? We did, right? So yeah, STRT. So by rewriting the type 2B supergravity, so yeah, we just introduced so-called axial Diraton coupling constant, not axial Diraton field, which is a combination of Ramon zero form and also dilatation field. Yes.
Didn't get to 13.4. So STRT.
Huh?
30.4 you haven't.
13.4, can you see? Oh, didn't I tell you?
No.
Oh, you didn't? I didn't. Oh, okay. Okay, sorry. Okay, then let's do that. Sorry. Oh, I didn't. Huh? But last time I remember that I told D1 is mapped to, huh? Sorry, D3 and D1 and D5 is the same as F1. Type 2 STRN type. So we didn't talk about this STRD. Here I'm going to talk about. But we talk about type. Can you see? Oh, 13.4, yeah, that's for sure. But I'm talking about now here. Oh, I'm relieved. I'm just, so, this is self-deal. So type 2B, STRT, enjoy STRT, and then under the STRT, D1, F1 is swapped, and D5 and S5 is swapped. And then this one, so this axial Diraton field, so this is Ramon zero form. It's mapped to, it's like a structure coupling constant, where ABCD is the SL2Z element. That's what we saw from supergravity action. Okay. And then this is indeed, so since the top, so vacuum excitation barrier, GS, is the vacuum excitation barrier string coupling the Diraton field. Once you set C0, is equal to 0, then there's the S duality 1 minus 1, 0, 0. This element corresponds to it brings the GS plus 1 over GS. Therefore, the S duality is the strong weak duality. Strong weakly coupled constant. How to say? Weakly coupled. Theory is equivalent to stronger coupled theory in type 2. Okay, and then so we already know this is oriented for projection. And then we briefly talk about this is their T duality. So let's read. Also again recap this T duality because it's important. I mean everything related by string duality. So heterotic, as I mentioned, for heterotic. HE and HO are so right mover are superstring. Left mover, so it's a heterosis, which is a mixture. Mover is the bosonic string. And then, so we just compactify difference between them by the 16-dimensional torus on 16-dimensional torus, and from here you get the self-Dale unimodular even lattice, which is the two candidates. One is 8 cross E8, as far as remember. The other is gamma. It's all 16. No, 16, 32. So that's the lattice we need to construct the boson on 6-dimensional torus. Okay, yeah. So then, if you compactify on S2 and on S1, then you add another torus 1, 1 and 1, 1. And there indeed, as a lattice, it's isomorphic. And then, so there is a modular space of this lattice, as I mentioned. It's like the higher dimensional version of the modular space of torus. So higher dimensional version of the modular space of torus. So lattice. The shape of lattice is parameterized by this coset group using the Lorentz group. O1 cross O17 divided by O1, 17. And at generic point, it reduces to the utility. At the generic point of this modular space, rank the gauge group is broken to U1 to the 18. I already forgot. I first remember 18. Yeah. So do you know where does 18 come from? It's broken to 8. Why it becomes 18? Can you tell that? Can anybody tell that? 1 plus 17. 17. That's true. That's true. That's true. Actually, so rank of E8 cross E8. E8 cross E8. And also rank of SO32 is what? Do you know what is a rank? The dimension of Cartan subalgebra. What is the rank of SO32? 16, good. 16. So remember that so SO32, so when it's SON, it's diagonalizable to this block diagonal matrix, right? Cosine theta and sine theta minus sine theta, cosine theta, 1, 1, 1, 1, and also the same piece here, but the theta 2 and theta 3 and so on. But it's diagonalized, no, it's not, sorry. Block diagonalizable by conjugate adjoint action. And this number of theta is indeed the rank of the SON. So SO32, the rank is 16, and the E8 you get the 16. That's why you get the, to get this one, oh, sorry. I think. So this is the 16-dimensional even self-field unimodular lattice, right? That's what we have found. So this 16-dimensional is really the rank of the gauge group. And then you add 2 more Lorentzian lattice, but you get the 18. So once you compact furthermore on S1, what you get is the rank 18. That's why for generic point, everything completely broken to U1 to the 18. But if you go to the the boundary of the modular space, it gets enhanced to E8 cross E8 times U1 square. It should be, yeah. And then another thing is the SO32 times U1 square. Okay, so that's so that once you put the S1, so there's only single lattice. But the question is, what is the shape of this one? The shape is parameter of this space. So that's why they are to each other. Oh yeah, so then, so once you compact by heterotic string, both it's okay on D-dimensional torus. D-dimensional torus, then modular space is further becomes SO D comma D plus 16. And then OD, and then O D plus 16 divided by O. It's a huge modular space. Okay. And then later D is equal to 4 will show up. And D is equal to 4 case will show up later. And then D equal to 4 will show up later. So just keep in mind. Now, so then we will show another singularity between them. So this there is still. Okay. So they are still each other. So that's what we're going to see. So remember, so type 1. So what kind of D-brane does it have? What's type 1 theory has? What kind of D-brane? Okay, so let's first start a very simple thing. Okay, you guys should know. What kind of D-brane do you have, type 2B? Good. D minus 1. D1, D3, and then D5. Okay. Okay, and then so if you take the oriented projection and you get type 1. And then which one will survive? Good. So it will survive D1, all disappear, and only D1 will survive. Okay. Oh, sorry. No, D5 survive. Also, huh? You should survive. Sorry. In fact, actually, D7 is non-dynamical. It exists, but it will go away. And then to get the, so we already see the tadpole cancellation. So you remember plus 2 times this guy plus so you put the orientifold, one orientifold, 09 minus, and then we put 32 D9 to cancel Raman charge. That's what we have seen. So the type 1, we have D1 and D5 and D9. Okay. So, and this will give rise, these two guys will give rise to SO32. Okay. And then heterotic, we already see this one has SO32. Okay, SO32. Okay. Or the gauge group coincide magically. And then you remember 32 really come from 2 times 5, 2 to the 5. Okay, 5 is a half a dimension. Okay, that's we already seen. It's very magically working. String theory. It's very it's very meticulous. So now let us recall what is a hydraulic string. Hydraulic string so what kind of object do you have? Hydraulic string, are there any D-brane or not? No. So there is no D-brane. Do you understand why? Why is there no D-brane? Can you give me the reason? Why is there no D-brane in hydraulic string? Just recall what we have learned. So I mean, string theory is very complicated, so it's better to recall. Why is there no D-brane in hydraulic? Do you remember? So Raman P form will give you P plus 1 form whose P strength is G P plus 2, and that is created by psi L bar gamma whatever mu 1 mu 1 to mu P plus 2 psi R. Okay, so remember. That is associated to the vertex operator, space-time vertex operator. So that couple to D-brane, DP brane couple to electric couple to this Raman flux. However, so hydraulic string, there is no ferment on left moving sector. Okay, so you cannot create a vertex operator corresponding to Raman flux. Indeed, so. I'm going to show you the supergravity action from now, but there is no Raman flux. So what kind of object does it have? Fundamental string, and then it's 5 right? That's it. So since this has a B field, so these are object, extended object. That's the hydraulic SO32. Okay. So now, so let me erase let me write down the supergravity action for type 2. It's type 1. Sorry, type 1. So gravity action is very similar to what we have before, but the supersymmetry is reduced. So now, both has, this, these are 60 superset charges. These are 32 superset charges. Okay. So then I'm going to write down supergravity action. Yeah. So which has the following form. So this is the gravity action. And now, so what is the difference between supergravity on type 2 to here? What are the difference? Can you make observation? What is the difference between type 2 supergravity and type 1 supergravity action? So gravity part, we just look at the gravity part. G3 theta is equal to dc2, and then there's Chong-Simons part, right? As far as I remember, yeah. I'm not going to write down everything, but anyway. So what G theta is essentially the field strength of this the Ramon 2 form. So what is the difference between type 1 supergravity and type 2 supergravity? Can you tell me? Type 2 supergravity action. So this is NS sector. This is Ramon sector coming from. So what is the difference? Type 2 and the type 1? Okay, good. Wonderful. So type 2, so it has a B field strength. So type 2, good. Good observation. Type 2, you always have B field. So you have a kinetic term for B field. But here there is no B field because after orient for B field disappear. So as you recall, so orient for the action, B field would disappear. So that's what we already seen in the orient for projection. So the difference is type 1, there is no B field action in SNS sector. And of course, this D1 and D5 is electrical and magnetic coupled to this Ramon 2 form, whose field strength is G to the SP. And another difference is also there is a Yang-Mills action, super Yang-Mills action, 10-dimensional, which is G to the 10 square D 10x squared minus G. And I already forgot what the e to the, I think e to the minus 2 phi f squared. What's the correct action? Correct action is e to the minus phi, and the trace of So this is Yame's action. So there are two parts of the action. So and of course this Yame's action is responsible for supergravity plus SO32 Yame's action. Super Yame's. Of course there is the fermatic part. I just write down bosonic part. Okay. But fermionic part is omitted. But so there is a super partner of the Yamels, Gaugino, and also super partner of the graviton and the dilaton, dilatino and gravitino, and so on. There is a corresponding action, but I'm going to omit fermionic part plus fermionic part. So this is action, and then so so omega 3 is indeed a Chern-Simons term coming from Yamels. Is trace of I think it's just notational difference between supergravity people and so on. This is Chern-Simons term, which is a bit different from what I have written yesterday in the differential geometry course, but they just after normalization. A goes to IA or something like that. Okay, so this G10 is Yame's coupling constant. This is Yame's coupling. Okay, Yame's coupling. Okay, so that's what we have. And let's look at this is the type 2-1 supergravity and heterotic SO32 supergravity action is a similar way, and it's very similar indeed. Let's grab. And times we have R plus 4 tabula mu and NSN is 5. So this is only half NSN is 5. NSN is 6. Okay, so then this is really NSNS sector instead of and this guy is really B field. Okay, so since heterotic string has F1 and S5, that couple to B2. Okay. So, and then you have the same, almost same Yame's action. A bit different normalization. Minus 2 phi, trace of f wedge star f. Okay, let's write down this one. It's also f wedge star f. So f is the field strength of the Yamels. Okay, so this is the heterotic 32 super SHO action, supergravity action, and the H2 is again it's the same, very similar. So H delta 3 is the field strength of B field, and shift by this transformation action. It's the same shift up to some constant. Yeah, it's the same. Okay, that's the shift we have. Yes.
The type 1 supergravity, the dilaton factor in your node is in the bracket. That's e to the 2 minus 2.
Then let's see. Let me think. Okay. I'm not sure which one is correct. Let me think now. Okay, so I think it should be outside in that case. I would imagine. Yeah, it should be outside when you compare with it. Okay. I think this is typo because when you try to compare with them, they should be. You're right. I think this is correct. Okay. And then you can see the already similarity between this action and this action. I mean, just even though this comes from Ramon, this comes from NS, you just swap between G tilde and also H tilde. That's the only difference after some factor. That's very similar. And then you have the same SO32 Yamada action up to some factor, and you can see, so they are related by the following field changeable. The type 1 is the just scaling of phi h, gh, nu. So just scaling of the, and the phi I is related to minus phi h. And the rest, you just do the scaling, and G3 here is the same as H together. 3. This is the hydraulic side, and this is type 1 side, and then the Yamada action is the same. Okay, so that's the difference between them. And I would imagine I missed something here. And then 2 and the minus sign. Okay, so if you do this Fourier change, one can move from one to the other. So in other words, essentially, so these change in essential. So the scaling of dilaton part and also sign change of dilaton and are not important. Essentially, what's important is just that C2 is changed to B2 under this S duality. So that's the essence of this S duality. And so therefore, you can just easily see, so since C2 just coupled to, I mean, D1, D5 is electric and magnetic coupled C2. On the other hand, you have F1 and S5 electric and magnetic coupled to the to B field. So this tells us that the D1 and then the D5 in type 1 in the under S duality, you have F1 and then S5. Okay? And this D9 and the O9 minus just give rise to SO32. Okay? Yamada. So therefore, it's a space filling. But if some space filling will give you just the same Yamada super Yamada action. So therefore, it's consistent. Okay, so that's the difference between them. So the reason why this is a duality is just negative sign here. So e to the phi I, phi I, the type 1 is GS string, is the same as 1 over GS is equal to e to the minus phi h. So therefore, since the string coupling is the e to the vacuum excited by a string dilaton field, therefore if you have a minus sign, you go to the stronger weak duality. So that's why it's called duality. Okay. We can do further check a little bit more. So remember, so if you look at the worksheet, how to say, worksheet action involve type 1. No, sorry, heterotic. Okay, so type 1. Okay, so let's say heterotic SO32. Then we remember that the xi of z and also its Fermat partner of z, and also that comes from right mover, and the left mover you have a Fermat construction, which is minor while, okay? And this will give you the S8b, 8b and HC of little group of the space-time of superstring. On the other hand, you have 32 vector of SO32. So that's we saw in the other worksheet action. So worksheet action, you have A runs for 1 to 32. And indeed, this corresponds to type 1. This corresponds to the spectrum of D1, and also here that corresponds to supersonic partner, bosonic. This is fermionic, bosonic, and fermionic, and this is D1, D9. Left moving fermionic. So let's look at the. How to get these number HB, HC, and so on. So now, for instance, if you consider this type 2-1, you have a 0, 1, 2, 3, 4, 5, 6, 8, 9. And D1, suppose D1 brain sits in here, and D9 brain sits in here. And the D9 brain is 32 of them, okay? So that's the configuration we are looking at. And then D1 brain is the space-time to the D1 brain. So D1, am I doing something stupid? Oh, sorry. I cannot count the in space-time, so it can end on D1 brain. And then, so the string has the fluctuation can to the normal direction. So it can fluctuate this normal direction, okay, which is 8-dimensional. So therefore, D1 brain has degrees of freedom that can vibrate on a normal direction. On the other hand, you need to impose a division rate on the 0-1 direction. So there is no freedom for vibrating on the 0-1 direction. So that will give rise to 8p, a bosonic, and then it's supersymmetric, so it should have a supersymmetric partner. And then 8s, 8c is the supersymmetry, coming from supersymmetry. On the other hand, D1, D9 brane, D9 is the space filling. So space filling, and D9 is, again, it's a schematic diagram. So the D9 space filling, D9 brane, but there's 32 of them. So one is end on D1, and the other is end with somewhere else. But there are 32 of them. Okay, so you have to choose one out of 32 space filling brane, and this 32B really come from the choice of which D9 brane that ends. So that's a choice you can make for D1 and D9 brane. And then the worksheet action that appear in heterotic, and there is a corresponding degrees of freedom in type 1. So that's another evidence to show that the duality between type 1 and heterotic of SO32. Okay, so that's the okay, so now one can ask the following question. So we know what is the stronger coupling limit of type A? Strong coupling limit of type 2A. If you take strong coupling limit type 2A, what's going to happen? Oh, come on. I already explained at the beginning of lecture today. Huh? So it becomes M theory. So 11 dimension will pop up. What is the strong coupling limit type 2B? What is the strong coupling limit type 2B? Yeah, good. Itself. So it's S duality. So if you take the strong coupling limit type 2B, it becomes itself. Okay. What is the strong coupling limit of type 1? What is the strong coupling limit type 1? Huh? HO, good. So it's a duality. So if you go to a strong coupling limit, it becomes a heterotic SO32. What is the strong coupling limit of a heterotic SO32? What is the strong coupling limit of heterotic 32? Type 1, good. Type 1. Okay, so what is the strong coupling of heterotic EH? We are going to ask. Okay. So we are going to ask this following question. What is the stronger coupling limit of the heterotic 80? What is so coupling quadratic E8 plus E8. Okay. So we will do the following very, very heuristic argument. So we know HO on S1 is SDL to type 1 of on S1. Okay, so that's what we already seen just now. And this is TLDL to HE on S1. Okay, but this is radius R, but then you have alpha of R. And what is TDL of this guy? TDL of type 1. We saw it, but do you remember? Yeah, type 1 prime. How do you construct it? It's also a construction. So type 1 prime is indeed so just recall that the so type 1 on S1, so you have circle and you have a bunch of D9 brane, 39 of them, D9 brane, 39, no, 32 D9 brane, and then one orient fold plane. O9 minus plane. And if you take TDL of this one, so you have instead, you have type 2, so type 2A on S1 mod Z2. Okay? S1 mod Z2. And then indeed a D9 brane becomes so S1 mod Z2 is essentially S1 mod Z2 is just a orientable orbital projection on Z2 action like this way, Z2, so that you have a segment. You have a segment, and then you have a so there's a 32 D8 brane. And then you have the 2 orientable O8 minus and O8 minus. Okay. So this configuration type 2A on S1 or Z2, we call it is type 1 prime. We call it type 1 prime. So that's a long time ago. 2 or 3 lectures ago, we just briefly sketch. So D9 under TDR the D9 becomes D8, and then under TDR the O9 plane splits into 2 O8 plane to preserve Ramond charges of O plane. And we call it this one is type 1 prime. And then we know type 2A, so if you take the stronger coupling limit, of type 2 on type 1 becomes M theory. So we know the type 2A, strong coupling in type 2A is indeed M theory on segment. So S1 mod Z2. But now the strange thing will show up. on, of course, type 1 is the D dimension, and M3 is, there's another M3 circle. This is M3 circle. We show up, so that the total is the 11 dimensional. But now, so let's see what's going to happen in the stronger coupling limit of this guy. So now, once you take M field limit, what's going to happen is as follows. So O8 minus and O8 minus is sitting here. And then half of the D8 brane moves to the on top of it on the one, and a half of the very magical property will show up. So the half of the D8 brane is go to this place, lots of them. So plus 16 D8, and also there's a 16 D, half of the other half will go to the other end. So if you have O8 minus and 16D8, what's going to happen? What kind of field do you have? If you have, so we know that 32D9 plus O9 minus will give you SO32 gauge group. And here, what kind of gauge group do you get? O8 minus plus 16D8, what kind of gauge group do you get? O plane will give you SO. O minus plane will give you SO. And since there is 16 D brane, so this will give you SO16. This will give you SO16. Okay. So the combination between 16D8 and the O8 minus plane will you get the SO16, and if you take if you go to the string coupling limit, so there's an enhancement. There's an enhancement will show up. It becomes E8 cross E8. That's a heuristic argument, but if you do this so-called Green-Schwarz anomaly analysis, you can check this is true. So now we have a very interesting situation we're encountering. So now, so this is R. Here, if you take a stronger coupling limit of type 1 prime, you have somehow E8 cross E8, which is the same gauge group from heterotic string. So it's very tempting to say this means this one, if you go to the strong coupling limit. So what's going to happen is as follows. So you have a 10-dimensional space. You have a 10-dimensional space. I cannot draw. 10D, D go to 10, heterotic E. And if you take the stronger coupling limit, GS, it's a similar phenomenon happen to the what happened in type 2 A to M theory. So when you take the stronger coupling limit, what you observe is another direction will show up. Okay? S1 direction, another S1 circle will show up, and it becomes 11-dimensional M0. The similar thing happened here, and now, so 10-dimensional, another direction will show up. So this 11-dimension, how to say, x is equal to 10, d equal to 11 dimensional will somehow emerge, and at the end of the, so this is indeed S1 mod Z2. So another direction will show up, and at the end of the this segment, you have a 10-dimensional space. So d equal to 10 and d equal to 10. But on the other hand, here you have the some combination between stronger couple limit of 08 minus and the 16D8. Okay, that will give you indeed so-called stronger couple limit. And if you take the stronger couple limit, coupling, okay, maybe GS goes to infinity, then it becomes another. So we're just looking at this path now. So when you go from here to here, another direction will show up, S1 will show up, and this becomes so-called M9 plane. That will give you E8 indeed. So M9 plane, and also, and then that will give you E8. And another, the other end of the wall becomes M9 plane, and then becomes E8. So namely, so here, at the end of the segment, you have some special thing occurs. So you have M9 and M9 plane. Okay, so the 9 plus 1 is D. And then magically you have the E8 gauge group on one side. On the other side, you have another E8 gauge group. So that's the prediction what the physicist has made, and then this length is indeed R, is indeed is G hydraulic coupling of 3/2 times L. Once you take the string couple limit of hydraulic string, so GS hydraulic, so you can see the another direction, and then stronger couple limit. So once you take weaker couple limits, this E8 plane actually squeeze them together, and at the end of the day, so once you take a weaker couple limit, you get E8 plus E8. So, and furthermore, once you take the this circle, the length of this circle to shrinks to 0, you can go back to the type 1 prime. So once you take the string coupling constant very strong, so this direction emerge, and then once you take the S1 direction to be small, you can go to type 1 prime, and this M9 plane is decomposed to 08 minus plus 16 D8, and the other M9 plane will decompose 08 minus plus 16 plus D8. So it's very magical, but so stronger coupling limit of the string theory, there lots of mysterious phenomena will occur, and then there is lots of supporting evidence that will give this heuristic argument. Yeah. So this one is the and this one is called hydraulic M theory. theory. And then so the reason why this M9 plane, or sometimes these M9 planes go, I mean, there are many more M9 planes. Sometimes it's called end of the world plane. Of world plane. I mean, really, it's a segment. It's a segment, and it sits on the end of the segment. So that's why it's called end of the world. And then this prediction was made by Hojava-Witten. So sometimes it's called Hojava-Witten wall. There are many names. M9 plane, end of the world, or Hojava-Witten plane, domain wall. Yeah. Okay, so that's the strong coupling. It's a heuristic argument, but one can do the so-called anomaly analysis to support this idea. Any question? Shall we take a rest in that case? So, break. Shall we take a break? Okay, let's take a break.
够离谱。我推到底是超级不低是不来。是啊，N0也没有说 action
DC 就是 TXT，其实这里的话是一个纯属对 Zeta 其实
他
是要
只是说这个
它
东西就它的 limit 啥可以连在一起是吧？
你好的，可惜，其实这里是个实数的。对，就是这里的 y 其实就是沿着纯虚轴，所以你这边有个 y，这边这个 I 就是你作为就相当于你 calculate 做 weight rotation， 排出来，1%就是这个 weight。
啊，下个回到图吗？
对的，本来是这样的。这个就是上面的，
我又是有卡的
C 就是 x 加 y。
那我也要去微调
他做的就是把 y
然后去的话，
考虑 y 在
算
y 的负平面上做一个 rotation，那就是然后你
把它拿给
它这里就作为计量代码可以看清楚一点，这个 y 就是
如果他不做的话，应该我觉得大概然后说有一个人，真的这次是上海的同学在，好上次后来我换了个考跟他讲，他说4名9友他以为我做慈善了，可法也听嘛，然后就觉得很弄一个他直接这么说，就当我哥那个上海那一家4名9友他以为我做慈善，然后不是想帮我意识到一个确实上海的休息还挺对的，可能经常干这种事情，那他觉得便宜，他别刮呀，他就是脑残，人他们填了自己发自己东西，现在都买多少钱？他双周领多少？原价44，加上4799，贵了350，所以算便宜的，价格。而且还是手比自己白，据说国行毕竟可以保，就说最早是2的计价去修，3个月内。所以上次说你评估这么差，PS王用很长时间，他们说疯狂放12月份的但是 Pro 手柄还真挺好用的，手感还真不错。我就店里试上 PS5的时候也是看在一拉不错。PS5我就玩过最爽的是试试 Pro 手柄拉，手柄手感还可以，还行。这个4就这么开的。那设计问题，它闹电也大呀，贼大好，唯一，但是这个呢，人说不可避免，摇杆来下去，摇杆是不可避免的，
又贵些。
这可以，就是透明设计，我现在拿一下。一家说11年多，我一正用摇杆，用摇杆来蓄力攻击，那不是折磨自己吗？打那个是这样，打街霸就是摇杆，操！摇杆搓招，摇杆搓招也有点难以接受，对我来讲，有点难以接受。比10件搓方便多好。 习惯了应该可以，但我要一阵子习惯。
我这个摇杆错了，当时很爽。
就是摇杆，比如说你要2连，现在低了，反正就
我十字键我觉得也都差不多。对。像这个 PS 手机实际上有些更好些，方法也差不多。
可以用 ThinkPad 红点作业。红点作业。那种红点会变很好。
现在还红点。
不知道，我也不买，更多是轻薄本。都是轻薄本。
我这个怀疑这个设计已经没了吧？这为什么会有红点这种设计？我现在有出版，那红点干啥？
就有些老人会习惯，没有就不行，就不买。太多了。我在想这些值得花4800买个 PS5。
是的。
啊？
是的。你要想想，能跑 PS5电脑值多少钱？
我不得这样。那我毕竟现在已经有700。
I just want to try.
发现那个在那个就是有个海南图片，可以在那个花条上，这边都是那种，就是整部都是那种棕色为基本，然后这边都是那种花条。
我跟你还有花椒，
然后都是那种那切。
Can you open?
先学旅行的，和飞机有在学，我两个都没学。
你不学啊？那个语言上啊，语言工作上你学不到什么东西。
他学不到嘛，是不是？他不讲。
他主要讲就是这个各种研究方法，就是给你分个路，然后就
之前的那个，那不就
感觉是文化。
这都是一年的热，除了量子评论是，不是除了运气的，第二个
就他真教你该怎么做，就算那个算是传播者啊，这样的话，我觉得还是
就比如这样就是啊。
接下来是区域的非常热，然后讲这个回场台的，然后回场什么的，然后在 QCD 吧，QCD 就只给大家的这样的这个，然后接下来是文化，文化会是没了，我们还讲 CFT， CFT 讲了一点。
现在讲，
现在没了，
上网了。
上网了。这个是3个的课，但是它每题是4个学时，每个星期4学时。都是事业考。
你上4节课也太紧了吧？
他说，就1周2次。
哇。我有2节课，第3节课也。我已经没喊了。
他那个课，主要是我现在没有学过那个，就接下来抓一个更难的。学过课就很简单，他讲的感觉很细，讲作业感觉讲的很细，
还讲作业。
是啊，
这样还有课会讲作业。
他那个作业都是不用交的，就是
看时光嘛。
他就是2
反正讲
然后上次讲这个，然后他还自己补充知道一个。
今天的教训。
那是呀，是那你不懂好吧？
就是怕你懂。
你懂，你学会了。还讲那个春话，春话是我倒没学好，没有搞懂那个。
你这怎么讲的？
但是跟那个不一样的，你用二冲的话，你说一话，它这个是跟那个没有就是那个在算维数这种话术前面两项，
我也是感觉好，还有相谱，
它是可逆的，一同二不可逆。
这是什么差别？
这种话说的话就是你会上信息，对，你每次做的时候。
Okay, shall we start? So even though it's a bit heuristic, we now see they're related by string duality. All the string theory are related by string duality. In particular, so once you take strong coupling, then you can go to another string theory. Some string theory. So if you start type 1 and go to string coupling, it looks like heteric SO32. It's the same vice versa. If you start with weak coupling limit heteric SO32 and go to the strong coupling limit, it looks like a type 1. And then if you take the compact file on the heteric E on S1 and then take the large strong coupling limit of the strong coupling, you become heteric M theory. But if you shrink S1, it looks like the type 1 prime. Type 1 prime, and then the length of the segment is proportional to coupling constant heteric string. So even though they have this different description, somehow once you change the string coupling constant, or which is Bucky expectation value of the atom, often another string theory description will become effective. So that's the string duality. And then we have seen that, and then we will see another string duality. We'll see. Okay, so other string duality, we will look at the following. There are lots of string duality, but another thing is this guy. So unfortunately, we don't have time to talk about the Calabi-Yau compactation, but I would talk about the simplest non-trivial Calabi-Yau twofold, which is called K3. So we are considering the K3 surface, which is K3 indeed come from. K3 is essentially a blow up of T4 mod. Um, Anyway, so just I would tell you, so it's some quotient of the four torus. So it's a real four-dimensional manifold. This is a real four-dimensional compact manifold. But it has some nice property, and it's more like a hyperkähler manifold. It's called hyperkähler manifold. And then the K3 comes from, oh my goodness, I should know, Kumar, oh yeah, Kähler. And then, what was that? Kodara. So this K comes from, K3 means come from three mathematicians' names, strong mathematicians' names. Kumar, Kähler, and Kodara. This is indeed actually hyperkähler manifold. And then this one's coined by but this K 3K come from these three mathematicians, but this one's named by Bailey, French mathematician. One of the greatest mathematicians in 20th century. And so, do you know K2? What is K2? What is the K2? Do you know K2? It's the mountain called, there's a mountain is called K2. It's in the Himalaya, at the Himalaya. I think it's the second topest. The one is, what is it in Chinese? It's Everest is the topest, right? Highest one. And the K2 is the second. I would imagine. I don't know. This one is famous for climbers that it's very hard to climb up. I think some rumor mentioned that it's hard to climb. It depends on, of course, the route, but it's maybe difficult than Everest. That's what I heard. So K3 show up as an interesting object, but it's hard to analyze. That's the way it wants to convey. So this mountain is very hard to climb up. So it's Bay just coined this K3, mentioned that it's a very interesting object, but it's hard to analyze. Nowadays, there are lots of techniques. There are lots of things about K3 is understood mathematically, but still there are lots of mystery in the K3 who give rise. So one is called moonshine. Okay, so it's a different topic, but the three Japanese string theorists, I think they are very famous. One is Kasoi. So they observed the elliptic genus of K3. So just the elliptic genus of K3. So you just consider only the same. That's 4,4 to this conformity theory. That will give you actually theta 1 top. Sorry, 2. I did 2 square or 4. I already forgot. Maybe some power. I think 4, as far as I remember. You can take a look at Wikipedia. Correct me if I'm wrong. No Wikipedia. I mean, you can just take a look at the paper itself. I think I already forgot. The year is 12, maybe. And that is related to so-called character of irreducible module M24. It's a Matthew group. That's the highest dimension sporadic group. It's called monster group. So it's somehow related to some representation of the M24 coming from K3. That's one some mystery that K3 gives rise. Let me check what I wrote is correct. I don't. It's recorded, so I just want to. Don't want to make a mistake, and so. Oh yeah, yeah. This is original one's correct. Yeah, so this somehow the K3 is a very interesting object, but it gives us lots of mystery. Yeah. Huh? 8 in front. Okay. Maybe one of them. So, and then Bay was correct in his side. Of course, I mean he's a great mathematician. So K3 is a very interesting object, and also it appears in string theory a lot. So I will introduce what is K3 is. What K3 is. But today I'm not going to talk about this one, mushroom moonshine. So this one is just some just detour. Maybe I can. What are the Chinese names of Keto Mountain? You know? Huh? So you can just Oh. Chocolate?
Yeah.
I see. It's more like a Tibetan. Come from Tibetan.
I think it's near to Pakistan.
So it's a local people call this one, like this way? Okay. How about Everest? How do you call it in Chinese? How do you write it? Can you write it? Can you write it? But this one, the local people call it this one, right? From Chinese side. No? Oh, gee. I see. I see. Interesting. But there's no meaning, right? There's no Chinese meaning. Huh? Tibetan. Right? Okay, good. I see. Okay, so what is K3? So let's start with T4, which is R4 or Z4, Z to the 4. Now, of course, this can be understood as the x1, x2, x3, x4 in the R4, and you just identify xi to the xi plus 1. So this is just T4, your familiar object, but now z direction x T4 as any coordinate simultaneously go to xi simultaneously. So just schematic diagram. So you have the it's very similar to what I explained yesterday from differential geometry course. So it's a schematic diagram of T4. Instead of T4, I can just draw the T2. This is a universal covering of T2, but so there's the origin here, and you just identify opposite point around the. So this point, the x is identified, whatever x is identified at this point, minus xi. So that's the identification you make. So this point is identified this point, which means around, I think around here. So this point is just around here, it's the same thing. And then, so at the end of the day, so you have so this right half is identified left half because of this this identification by Z2, and there's a fixed point. The fixed point is the x is either xi is either 0 or 1/2. So you can see there's a fixed point in 4. This fixed point of this interaction is indeed this one. That you can see. So 0 goes to minus 0 on the Z2. But this one is equal to minus 1/2, which is the same as 1/2. It's therefore it's fixed. Okay, and so there is a 4 coordinates. So at the end of the day, t to the 4, which is 16, fixed point. So there's a fixed 16 points. So here, this diagram is like only 4 of them because it's just 2 dimension. But then there's another other 2 dimensions, so 4 times 4 is 16. So there's a 16 point fixed point. And then we will get rid of this. So we will do the so-called blow up of this singularity. So if you take the quotient of this C2, it's a 16 singularity. So this 16 fixed point becomes singularity, singular points once you take T4 or Z2. If you take the Z2 quotient, so we want to somehow make it smooth. You need to make it smooth. And the procedure is following. So you just take a look at the neighborhood around the fixed point. And then, so what is the topology around this fixed point? What is blue circle? What this blue circle become? So just point inside a neighborhood around the point inside a T4. What does this blue circle become? You have a 4-dimensional space. You have a point. You just look at around there. So what this blue circle? Huh? No, you just only look at the blue circle. inside at the T4. It's very same thing. If you look at R4 and there's a point and just look at the neighborhood. What's this object? S3. So this blue circle is indeed S3, and then you just so the detailed action just identify the opposite antipolar point. This point is identify this point, and then this point is identify this point. Okay. So the neighborhood it looks like S3 mod C2. What's this? What's this object? Huh? Good. So this is Rp3. It's if you identify the antipolar point, it becomes Rp3. So now, so to make it smooth, what we're going to do is as follows. To get rid of around the neighborhood of singular point. The same, you do the same thing for around this point and this point and this point. Just get rid of singular point. Okay? And there's a, if you get rid of it, so there's like a 16 boundaries, which 16 copy of Rp3 will show up as a boundary, okay? As a boundary. And now, so we want to fill out something in here. We want to something make it smooth. So we just get rid of it and just smooth the object we want to fit into here. So what we are going to do is as follows. You just consider so tangent bundle of S2. Okay? A tangent bundle of S2, then sorry. So you just consider tangent bundle S2. So you consider S2, and at each point you have a tangent space, and you just consider it as a boundary. So that's a tangent bundle. And then, so what are the dimension of tangent bundle S2? Real dimension. Tangent bundle as a whole manifold. Four dimensional. And then at the fiber is just at each fiber is R2. So each fiber is R2. And then just look at the unit circle at each fiber. Okay. Okay. So what we are going to do is just the schematic diagram. So you have a S2, and at each fiber you have at each fiber you have at each point you have a fiber, and then you just collect the unit circle, okay, and it just move around. So at each fiber, a tangent bundle, at each point you have a fiber, and just look at the only unit circle, okay, and at the end of the day, so at the fiber you have just get rid of circle, so which is one-dimensional object, and S2 is two-dimensional object. So you get it becomes three-dimensional object. So therefore, so you just consider a unit bundle. So or more precisely, so and you only look at the inside of this circle. Sorry. Okay. Unit circle, and the boundary you have a circle, which is the three-dimensional object. And then, so you have a unit circle bundle. So unit circle bundle V. Let's call V. And then indeed, so if you consider this, so unit maybe disk bundle inside a tangent bundle S2, and then at the boundary of V is three-dimensional object. Indeed, this is become Rp3. So we have V is in the four-dimensional object with boundary Rp3. So we can just now fit this B inside of this blue circle. At the boundary you have a Rp3. So you can identify the boundary of V as Rp3 and fill this, what you get rid of it and just fill this unit disk bundle inside this blue circle. And indeed, this unit disk bundle is smooth. Okay? There is no singularity. So just bring each singularity, you just bring V inside here. And at the boundary, you have Rp3, so you can identify it. You can identify this blue boundary and the boundary of V. So that is an identification one can make. So then at the end of the day, so the T form of T2, there is 16 singularity, as I mentioned, and everything becomes smooth. That is called K3. So that's how you construct K3 surface. Yeah. Algebraically, there's a lot of construction. For instance, if you consider CP3, you have a stereographic coordinate, which is the point is Z1, Z2, Z3, and Z4. And if you consider some surface, Z1 to the fourth plus Z to the fourth plus Z3 to the fourth plus Z4 to the fourth is equal to 1. If you consider such a surface, you will get the K3 surface. This is some algebraic way to construct K3 surface. I mean, if you are algebraic geometer, this is one way to construct K3. But I'm not going to go into detail. But I just give you some topological construction, how to construct the K3 surface. So this is the K3 surface, smooth real 4-dimensional surface, and which is hyperkähler manifold. So hyperkähler manifold means so real 4-dimensional compact Calabi-Yau manifold. Calabi-Yau manifold is either T4 or a K3. Compacts may be smooth. Is T4. Calabi-Yau is indeed Ricci flat. So the Ricci flat or C1 of tangent bundle of manifold is equal to 0. So there is zero condition of a Calabi-Yau manifold. And there's only two of them. One is a very simple one, T4, we already see, T4 compactation. Another is K3. Yes. Huh? Compact already means close. Compact means close without boundary. Oh, sorry, you are right. It's close. No, sorry. Close means compact without boundary. Sorry, you're right. Thank you very much. Okay, thanks for pointing out my mistake. Now, let's look at the topology of the K3 surface. So let's look at the K3 homology group of K3 surface Z coefficient. So it's closed, so let's go P, when P equals to 0, and the Poincare hole. So the interesting thing appear in the second homology group, and indeed, the interesting thing. The first of all, so let's analyze second homology group. And first of all, the interesting show what is the homology group, second homology of T4 of Z coefficient. What is the second homology group of T4? So what is the homology group? First homology group of T2. C plus C. How do you see that? What? So T2 is given by S1 cross S1. You pick one of them, right? 2 out of 1. 1 out of 2. How about this one? What kind of 2 cycle you can have? T4 is S1 cross S1 cross S1. What kind of 2 cycle does it have? For instance, what kind of generator of H2? Can you give me one example? One example of 2 cycle inside of T4. What is the 2 cycle inside of T4? Huh? Torus, T2. Good. Which torus do you want to pick? Can you give me one example of 2 torus inside of T4? Which 2 torus you would pick? Or can you give me one example? Yeah, first 2 is 1. Okay. First 2 is 1. That in this schematic diagram, this corresponds to this. The choice are here. Okay. Another choice is something like this one. This is another element of T2. So therefore, this is indeed 2 out of 4. Okay, 2 choose out of 4. Choose 2 out of 4. So you just pick 2 S1 out of 4, which is 4 times 3 divided by 2 means what? 4 times 3 divided by 2 is 6. Okay, so there is 6 tori inside. So therefore, H2 of the T4 is actually 6. Okay. Z to the 6. Okay, Z to the 6. So on the other hand, we now so this 16 in this schematic diagram, so this 16, so the one cycle is like this one. One cycle is something like this one. Another cycle is this one. But here, we fill B inside this unit disk B inside here. And if you look at this one, it's just the unit disk bundle inside a T cotangent, tangent bundle S2. Okay. So what is the second homology of the tangent bundle S2? What is the second homology of tangent by S2? tangent bundle is deformation retract to S2 itself. It's a 5 direction, just shrink to the point. So what is it? H2, second homology of the tangent bundle S2. What is the generator? Good. So it's just a two, generated by its two sphere. So H2 of S2 is C, right? So it's a top component. It's just generated by its two sphere. It's deformation retract to S2. So it's just C2. And you have a 16 copy of them. 16 copy of them inside of each blue circle. Therefore, you have a 16 copy of S2 in addition to this 2 torus 6. Therefore, so you have a 16 plus 6. This is Z plus 22. Z22, which is 16 plus 6. I mean, if you want to do some string theory or like Calabi-Yau compactification, this kind of analysis you have to do by yourself. And then, this is indeed Calabi-Yau. So you might have this is a Hodge diamond. You can just create. You might have heard of a Hodge diamond. Yeah. What I'm writing. So sorry. Hodge diamond H. And this is indeed equal to C, and C, 0, 0, 0, 0, and plus 20. As far as I'm concerned. Am I correct? Yeah, good. I'm correct. So this is a Hodge diamond. So this H00 Z will give you this guy, P equal to 0. And if you look at this horizontal line, if you total is 22. And this plus this plus this will give you, Dirac sum of this guy will give you Z to the 22, 22-dimensional second homology group. And then that last one will give you the top component. So that's called Hodge diamond. In the Calabi-Yau 3, 4, it becomes a bit bigger. Oh my goodness. Should I erase here? Okay. So what you learn differential geometry course is very important. So in string theory, so you have to be fluent about the differential geometry. So and now, so you have an intersection form in H2. So you have the homology group. You have a cup product you can take. Sorry. So I think I should write down the cup product times go to C. Okay, maybe I should write down more precisely. H2, Q3, and C goes to C. Such a way that the alpha and the beta is the element in here. You have to take cup product and then take the K3 itself, not your pairing. So you have, sorry, it's a two-cycle. I think I should go to Poincaré. So you have to take the product of two homology, second homology group. If you take up, or maybe in dynamical homology, it becomes wedge product. It becomes fourth cohomology group. So therefore, you can integrate fourth cohomology group on the K3 surface itself. You get Z. So that's called intersection number. Sorry. So this is, I call it Q. Q. So this is called intersection pairing. Intersection pairing. It's very simple. I mean, if you do T4, okay. So if you pick the T2 torus in the first component, what is the another intersection pairing? Non-trivial intersection pairing is this guy. Okay. So alpha and the beta. If you take cup product, you have a non-trivial intersection pairing. The same thing. If you pick the middle two, the other non-trivial intersection pairing is the other two. Okay. That's how you get the intersection number. So you can have the intersection pairing in second homology group. We now have its 22-dimensional, and it is not the intersection pairing and non-degenerate in compact. Cross manifold. So this intersection matrix becomes the following: E8 minus E8. And then sorry, I think I should write down like this way. Minus E8. And then 1, 1, 1, 1, and so intersection matrix become like this one. It's 22 times 22 dimensional matrix. 22 times 22 dimensional matrix. But this is 6 by 6 matrix. This is 16 times 16 dimensional matrix. What are the bases? How did I take bases here? What this 6 by 6 matrix stand for? How do I take them? What are the bases here? And what are this 16-dimensional bases here? So we just look at the 22-dimensional second group homology group. What this 6-dimensional, what are the bases? Here. What are the bases here? These six-dimensional bases of H2. Yeah, good. So it comes from the 2 to the 6 here, and another 16. This another 16 comes from this S2 here. S2 here. 16 copy of S2. And then the intersection matrix, it becomes like this way. The E8 here is Cartan matrix of the, so this is Cartan matrix of E8. Which I have written in heterotic string. I'm not going to write down, so it becomes 2, 2, 2, 2, minus 1, like this way. And at some point, you have some anomaly. I have minus 1, something like this. For E8, like this. This is Carter matrix I have written down. So this is E8. So it's a I'd say 8-dimensional, 8 times 8 matrix. So this becomes Carter matrix. Okay. And now so you have a hot star. It's hot star up to H2 K3 R to H2 K3 R. Okay. So alpha is mapped to hot star alpha. Okay. Then so we know hot star square is equal to 1. Okay. So we know hot star square equal to 1. So therefore it becomes the matrix which is just a plus 1, plus 1, plus 1, and minus 1, minus 1. So indeed, it decomposes under the hot star in 22-dimensional matrix. It becomes 3 plus 1 eigenvalue and 19 minus 1 eigenvalue. So it decomposes H2 of K3 of R is decomposed self-Diel form under the hot duality or under self-Diel form in hot star. And then this is indeed becomes 3-dimensional, R 3-dimensional, and another 19-dimensional. So this is self-Diel and anti-self-Diel. Self-Diel and anti-self-Diel. So that's the topology of K3, and now we just look at the modular space of K3 surface. So again, so as I mentioned, so T2, the modular space is H mod SL2Z. It's complex 1 dimension. And then T4, you have a similar thing. You just consider, the modular space of my modular space of like, how did I write down genus 1 is equal to this one. So the similar thing happens. So you have just considered lattice, which can be understood H of, let's see, it's hard to tell. That's hard to and then you have a mapping cross group of T4. This is the modular space of T4. So you have so this one is equal to R plus, maybe I call it plus in downstairs, times R. So which is upper half plane. So which takes the lattice, this tau, complex tau. And then you just take the mapping classical function of the T2. The similar thing happens modular space T4. You just consider lattice structure on the upper half plane, 4-dimensional operation upper half plane, and take the mapping class group of T4. And then you can consider the modular space of K3 surface. And this one is indeed related to this related to this second homology or second homology group, and this is indeed equal to times O 319 O3 and times O19. So this is more like corresponding to this is more like corresponding to this part, and then you have a mapping cross group action. Let's see. So that's indeed modular space of the K3 surface. Yes.
For torus case, the MCG should be PSL.
Yeah, you're right. Actually, this is more precisely PSL. Thank you very much. Okay, so that's the modular space, and so this is so this is Teichmüller space. Teichmüller space of the these are Teichmüller. And here you have a modular space of the K3, and this is Teichmüller space. And this one is a parameter size of or it's more like Kera parameter of K3. Yeah, overall size of K3. Okay, so this is what the mathematician has observed about the modular space of K3 surface. But now, so Aspin or Morrison in 1995 or 96, I don't know which one it was. So they considered, so this is classical Teichmüller modular space, but Aspin or Morrison would tell us that we need to incorporate quantum modular space. So we need to incorporate the effect of B field into the modular space. Yeah, actually, I don't need to. So you need to incorporate. In fact, so the effect of B field. So B field, the flux. So you have a B field, and each cycle, H2 of K3, Z cycle, the cycle, just pick cycle, cycle C2, and you just integrate over B. That will give you some parameters. So let's go I, 2 cycle I. You have so there's a 22 parameters. So this will give you 22 parameters. So because the second homology group is the 22-dimensional. Indeed, so this one is 58-dimensional if you do the analysis of Gaussian model. And you can just have the 58 plus 22-dimensional, which is in total quantum modular space should have 80-dimensional. So for quantum modular space. Indeed, the stringy or quantum modular space or stringy modular space. People maybe sometimes stringy modular space because its B field is stringy object. And indeed, the M stringy of K3 is indeed what the asking of Morrison will tell us that the 422 divided by all 4 times all 22 divided by 22. So if you incorporate this B field, this modular space is get enhanced, and bigger space, it becomes bigger space, and it becomes like this one. And this is indeed equal to modular space of the hydraulic string on D4. So recall that the so once you compactify hydraulic string on TD, so modular space becomes then you get D comma 16 plus D lattice, and indeed this modular space is indeed it becomes like this when D go to 4. When D go to 4, it becomes like this way. Oh, sorry, 20. Sorry, you're right. So that's what Morrison would tell us about the modular space. And this was indeed predicted by Witten's original paper. That from the following observation. So now we just look at the relation between hydraulic on T4 and type 2A on K3. So let's look at so if you do the compactification, so again D-dimensional, D is 10 minus 4 is 6. And look at the supergravity action of this hydraulic on T4. Then what we get is S hydraulic of 2 copper 6 2, and then D6 4 2 5, and they have usual Ramon. No, sorry. NS sector. Okay. NS sector. Supergravity part, and also you have the Yang-Mills part. You have a Yang-Mills part. So as you recall, so if you have you start with the heterotic E8 cross E8 or SO32 and compactify on torus T4. So the rank becomes 16 plus 4 plus 4, which means 8, which means U1 to the 24. At the generic point of modular space, at the generic point modular space, everything broken to U1, and the rank is 16 plus 2 times 4. Okay, the lattice becomes the left moving and right moving sector. You have to consider. So 4 plus 4, which is 8. So everything broken to the U1 to the 24. The gauge group is U1 to 24 at the generic point of the modular space. So therefore, you have a Yamil's action is indeed just Maxwell and the 24 copy of Maxwell action. Okay? And then you have a supergravity NSNS sector. So that's a supergravity action of heterotic T4. And let's now look at the K3 on 2A. So now K3 on 2A on K3. So supergravity action is again the same thing happen for Ramon NSNS. I keep mentioning NSNS. 3, 4, 6 of x minus square g, and then 3 minus 2 5 are so usual 1 and here 3 square, and this is an SNS sector. S and an SNS, here is also an SNS. And something so interesting is show up. So you have in type 2A, you have the so Ramon field strength is the C1 and the C3. So recall of the type 2A, so you have D0 brane and D2 brane that couple to this guy and the D6 and D4. So these are electrical and magnetic coupled to Ramon 1 form, Ramon 3 form. And now C4, the part is very, C4 is, I don't remember how I call it, it's, yeah, G to the 2. G to the 2 square. Okay, G to the 2 square behave like more like a Yamil's. It's more like a Yamil's. And now, and then we have a 3-4 flux, 3-4 Ramon field. But if you compactify on 2 cycle H2 of I, so the 2 cycle written over there. What did I write? 2 cycle. This is 22 dimensional. This is 22 dimensional. That will give you rise. So C is now cycle. So maybe I think I should call it some other name. I don't like. Maybe sigma. Sigma. Maybe I call it sigma. If you wrap the, how to say, if you 3 form flux on the body on 2 cycle, what's left is indeed it becomes 1 form. So you just integrate two indices out of the on this 2 cycle on the K3. So that will give rise to 24 ion for 1 to 22. Okay? So therefore, so you have, so I call it, maybe I should call I. So these three, Raman 3 form compactified on 2 cycle in K3, on K3. So let's go K3. Inside of K3, you have a 22 gauge field. And one is come from here, and then another come from the Hodge-Dill of masses. Yeah. So another come from, if you don't compactify on Hi2, and that is Hodge-Dill to, and that is dual to the H. Massless vector. So let's go 0. I equals 0. In Hodge-Dill. In D equals 6. So recall that the what you need to do is take the 3 form and then take the field strength G4, which is DC3, and take in 6 dimensions Hodge-Dill becomes G2. So this is a Hodge-Dill. Hodge-Dill is the G tilde is the G4, okay? And this can be understood as the field strength of some other I equal to 0. It's one form, okay? One form. So it can be understood this degrees of freedom without wrapping anything on K3. Just compact and just do the 6 dimension. It can be compensated by one form by taking Hodge-Dill. So therefore, in total, you have these Raman 1 form and Hodge-Dill of C3, and the compact forms are C3. In 22 of them. In total, 1 plus 1 plus 22 is 24, which is the same as the rank of the gauge field in hydraulic on T4. So therefore, so if you combine them together effectively, what you get is indeed in minus 1 over. Well, I think I should take a look at it. It's up to some factor. You have to be careful of a factor. Copper 6(2) over G C6. Unfortunately, time is over. 24, and the I stands for 1, and the Fi and 2, and square. And after feed application, you can just compare this one and this one. After factor of the some dilaton scalar field, you can just identify this supergravity action 60 and supergravity action 60. And this F2I really comes from Raman 1 form and Hodge-Dill of Raman 3 form and the compaction 2 cycle of the 3 form. Okay, so that's how you see the duality between type 2A on the K3 and then hydraulic on T4. Okay, so let's stop here.